Our starter problem for today, we got an Atwood machine shown, and we want to determine the time it takes for this 12 kilogram mass to fall 0.75 meters if it also has to lift up a 10 kilogram mass on the other side. And we want to know how much work is done by gravity on this guy and how much work is done by gravity here. So I already did the given. Let's do the find right next to it. So for A, we want to solve for T. And that's kind of a review. For part B, we want to know how much work was done on the, I'll just put little subscript there, a 12 for the 12 kilogram mass. And then see how much work was done by gravity on the 10 kilogram mass. Work done by gravity, And let's solve it. Let's do that up here. Well, if I want to know how much time it takes, that means I need to know what the acceleration is. And if I want the acceleration, that means I'm going to have to use the procedure with force, the Newton's second law procedure. And so I'm going to go ahead and do that. I'm going to straighten out the free body diagram because it makes everything easy. So I'm going to take this 10 kilogram guy and go whoop, put it way up here. So here's our 10 kilograms. And we've got gravity pulling it up now. All a stationary pulley does is change the direction of a force. So in our imagination, we can change that direction. And then here's our tension force that we don't really need. Here's 12 kilograms. And we've got gravity pulling this guy down. I'm going to make down this way the positive direction, positive y. Just because I know that's the direction of the acceleration. This is well, I'll call this object 1, M1G, and this is M2G. If I sum the forces in the y direction, I'll get MA. So I'm just following the procedure here. And in the positive y direction, I have M2 times G, and then in the negative y direction, minus M1 times G equals, now this is my free body right here, so I have to have the total mass of the free body, so that would be 22 kilograms, or I should put M1 plus M2, I guess, times A. And now I'll plug in the rest of the numbers. M2 minus M1, and we'll just do it like that. M2 is, well, oh, I switched the subscripts. Okay, this is the 12 kilogram mass. So we got 12 kilograms minus the mass of the small, minus 10 kilograms. I just factored out the G. Divided by the total mass. And so that acceleration will be, let's see, 2 times 9.8. And then we're going to divide that by 22.0. 22. And I get 0.89. 0.891. I guess I'll keep 3 significant figures here. Meters per second squared. Everybody agree with that? All right. So we know the initial velocity is 0. We're trying to solve for time. We don't know the final velocity right before it hits, and we don't need it. So I'm going to use the third kinematic equation since I don't need the final velocity. Delta y equals V naught T plus 1/2 A T squared. So this is 0. T equals 2 times delta y over the acceleration, the square root. Now I did something kind of funky here. I said positive y is down. So this from here to here in my, because of this, it's a positive delta y. I could have made up negative, and this would have been a negative acceleration, and the negatives would have canceled. 2 times delta y is 0.75 meters. 2 times, and then divide that by 0.891 meters per second squared. So T is equal to, oh, how does this calculator work? Square, oh, I see. So 2 times 0.75 divided by 0.891 equals, I get 1.53, and then I take the square root of that, and I get 1.24. Does everybody agree with that? We did it? Okay. So that's part A. Now part B, you want the work done by gravity on this guy. And this is fairly easy. I always, hey folks, I'm just going to get in the habit. I want you to get in the habit. I start off with the basic equation for work, which is F dot dr. And then I notice, look, for this guy here, the force of gravity is down and my displacement is down. And the force is a constant. So all this complicated stuff goes away. The dot product goes away because they're parallel. So I can just say that this is just mg times delta y. Here's the force, and there's your delta y. So I'm just going to say 12 kilograms times 9.8. I'll call it newtons per kilogram instead of meters per second squared, because I like to do that. And then delta y is 0.75 meters. And when I multiply all that out, I get 88.2 joules. And that's my answer for part B. Does everybody agree with that? You did the problem? Yeah, let's do part C. Now, one thing about part C is a little different. If I look at this guy, the force of gravity is down. Yes?
I have a question on B. Why would the acceleration be 0.89? Isn't the acceleration resistant?
This acceleration, why is it 0.89?
No, why in B, why don't you 7.89?
Oh, because it's, yeah, it's a force, yeah. So the question was, you know, for those of you listening online, the force, the question was, why don't we use the acceleration we calculated from part A right here? And that's a good question, and that's a mistake students will make sometimes. And the reason is that we want to know, what is the force on the 12 kilogram object? And the force is, and we want to, I mean, because we're asking, what is the force done by gravity? That's the key idea. What is the force, I mean, what is the work done by the force of gravity? And so you have to apply the force of gravity, because that's what we want to know, the force, we want to know how much work it did. So let's go to this one here, M2, or the 10 kilogram mass. it's being pulled down, but the displacement is up. And I always like to draw the force and displacement vectors just to make sure that I'm doing this right. Because now, when I apply the dot product, the work, well, I'll put in the mass. I'll just put in the, I've got the equation here. 10 kilograms times 9.8 newtons of force per kilogram of mass. That's Earth's gravity field. Times delta y. Well, it's going to go up 0.75. If this goes down 0.75, this is going to go up 0.75. But here's the thing. When you do the dot product, this delta y and this force are in opposite directions. And so the angle between them is 180 degrees, and the cosine of 180 degrees is -1. So negative work is being done here. So let's go, oh, that's just 98 times 0.75. And we get negative 73.5 joules. So that's, we've solved the whole problem. Now I want to ask you a question. Gravity did 88.2 joules of positive work on this guy. Gravity did negative 73.5 joules of work on this guy. It's not the same. Where is that energy? Where is the difference in energy? What did it do? In other words, where did the net work go? Any ideas? Yeah? What's that? Not yet. Not yet. Let's look at it just before this guy hits the ground. So the answer was heat, or the vibrations of molecules into the environment, dispersed into the environment. Not quite yet. Yeah?
Would be the acceleration?
Well, acceleration is not energy. It is, but the idea does fall into that. Yeah?
Does it go into the pulley?
No, not pulley. It's massless, frictionless, magical pulley. Yeah. Bingo. Bingo. Kinetic energy. Just before this guy hits, this guy is moving, and this guy is moving. And if you figure out what their final velocity is and go, 1/2 mv squared plus 1/2 mv squared, you'll get the difference. If you add this and this, you'll get, well, what is that? 88.2 minus 73.5. You get 14.7 joules. I challenge you, I'm not going to do it here because we have other things to move on to, but figure out what the final velocity of these guys are, and then do 1/2 mv squared plus 1/2 mv squared, add them together. Remember, there's no such thing as negative kinetic energy. And you'll get 14.7 joules. And that's where all the energy is. So, anyway, isn't that special? That is all.